Okay, let's start with the second part of semiconductors. And on Friday, we'll start magnetism. There'll be a couple of magnetism lectures. And then for the last week, I'm not sure whether it's written in the module, normal and advanced will be separated. So the advanced will stay here and normal will have a different lecturer and go to a different room. That will probably be announced later on. I'm not sure which room that will be in yet. So just to let you know, just do a little bit of different material. Okay, so let's continue on with semiconductors. I remember Andrea asked a question. Unfortunately, she's not here, but she'll see the slides anyway, about the temperature dependence of the band gap. And yes, it is dependent and it does decrease as a function of temperature. So what's plotted here is for 3 different materials. The usual examples or common examples that we have is germanium, and that has a band gap here of 0.7-ish EV, so quite a narrow band gap semiconductor. Then silicon 1.16 and gallium arsenide a little bit larger. So at room temperature, the values are shown there, and these are the values that we are very familiar with. But as you increase the temperature, they do decrease slightly, not very much, by about 0.2 or 0.3 EV by the time you get up to quite high temperatures. And that's due to phonons. Phonons are responsible for a lot of mechanisms and properties in materials. Remember we had that potential energy surface? When 2 atoms are interacting, we had the minimum in the well, which gave us the equilibrium lattice constant. But remember, as the atoms came apart a little bit, the potential wasn't perfectly quadratic. It was a little bit asymmetrical. And when the atoms get some energy, they vibrate more and they get energy and they experience the potential well that's a little bit asymmetric. So the atoms experience this thermal expansion. So the atom is a little bit further away from each other, and so that the potential that they experience from the other atoms is a bit weaker, and that gives rise to the slight decrease here in the band gap. More details are given in Ashcroft and Mermin, but at the moment you don't need to know any more than that, at least for this module. Okay, so that was a nice question, and yeah, something I wasn't planning to talk about, but yeah, that's great that it stimulated this new bit of information. Another thing, like these are the electronic band structures. Again, a common example, silicon and gallium arsenide, 2 really very heavily used semiconductors in the semiconductor industry. I want to just highlight the notation of heavy holes and light holes. You may hear about them, you may have heard about them, I don't know. But you know, this is where the holes are, your hole carriers. And you can see that at the top of the valence band, there are actually 2 bands for this material. And the top branch here is called that of the heavy holes. And you can understand that because you can see the curvature is really small. So the effective mass will be very large, and very large effective mass, that's probably how, yeah, the word heavy, because it's heavy, large, big, okay? And conversely for this, the light hole band, it has a very high curvature here, so it'll have a very small effective mass, hence the word light. And you can see that both of these semiconductors have these kind of characteristic heavy bands and also these light bands there. So heavy holes and light holes, okay, that's some terminology. Remember yesterday I wanted to show you a slide on the overhead and I couldn't get it working? Well, here it is, what I wanted to show you. I presented a table with some effective masses in. If we look, for example, remind ourselves about germanium, the values in the table were 0.6 for the electron, the effective mass of the electron, and 0.22 for the effective hole mass. So I want to just give you an idea of what the corresponding band structure kind of looks like. So this is an indirect semiconductor because the conduction band minimum is not at the same location as the valence maximum. And you can see here that the curvature of the band is very small, or it's smaller than this curvature, so you get a larger value of the effective mass there. And this has very sharp curvature, so you get a smaller effective mass there. Kind of similar for the silicon. And yeah, what I wanted to show you was this different kind of behavior for the gallium arsenide, where we remember we had quite a very different value of the electron effective mass, 0.065. So it's quite a bit different to the silicon or germanium. And in this case here, you can see that the conduction band minimum is at the valence band maximum, so it's a direct semiconductor. And you can see this is really very sharp curvature here, so you get a very low effective mass. Okay, so that's to kind of explain that. Okay, so now you can do a little bit of thinking. I'm going to show you some more band structures. Okay, so if you are given kind of all of these band structures to look at, some of them are direct semiconductors, some of them are indirect semiconductors. Have a little look at it and see if you can identify which would have the lowest electron effective mass. Okay, I'll give you a couple of minutes to think about it, and I just want to see whether you're getting it. I'm sure you are, but you can have a think. Anyone want to call out something? Or is it too easy? Oh, nobody. Any guesses?
I think it's because our feed like just behind. So
What's that?
like a couple of us our feed like just behind.
Oh, look, that's okay. Yeah. Well, okay. Let's just go on to it. Okay. So first of all, what do we here? A semiconductor. Okay, it's got a band gap. They're all semiconductors. Lowest electron effective mass. The first important point is, okay, electron. So you know that you are looking at the conduction band because that's where the electron carriers will be excited up into. And, okay, lowest effective mass will be gained when you have the highest curvature. Okay? Yeah, so all you have to do is look and see which ones have the highest curvature up in the conduction band, and you can probably see that, yeah, this one has a very high curvature, and this one here. So I don't really expect you to be able to tell those two apart because there's no numbers, but yeah, just like we had before, those are the two. Okay, just trying to get you talking a bit as well. It's okay. Okay, another thing just to get you talking and thinking. Remember we had silicon, and we're doping the silicon with various atoms, phosphor and aluminium. Now you've got a compound semiconductor, a gallium arsenide. Again, it forms 4 bonds, and so you're going to be doping it with silicon now. And if the silicon atoms are replaced or placed on some of the gallium atoms, obviously not all of them, because you remember in doping we just have very small concentrations of the dopant atom. But if we place a silicon atom on a gallium site, will the silicon act as a donor or acceptor? And if it acts as a donor, the material is said to be N-type, because N kind of means electron here, or is it P-type? Okay, so first of all, we're considering putting silicon on a gallium atom. Any thoughts? Okay, we know silicon's got 4 valence electrons, right? Gallium has 3 valence electrons, and arsenic has 5. So that altogether they have 8 electrons, 4 bonds. So the bonds are perfectly filled by sharing of the electrons. Now, if I take away gallium, which had just 3 electrons, silicon's got 4, so it must be a N-type. Yeah, excellent. Because there's an extra electron from the silicon that doesn't have a bond to go into. So instead, conversely, you can probably already guess the answer. If we put the silicon atoms on an arsenic site, will gallium arsenide, namely doped gallium arsenide, be N or P-type in this case? Yes, P-type. Because silicon has only 4 electrons in its valence and arsenic has 5. So we're just one short. So there will be a hole in our material. Okay. This diagram just kind of summarizes a little bit what we've been looking at. If we look over here, we just have schematic of our semiconductor, valence band maximum, conduction band minimum. Okay. Here, if we just look at the first one, intrinsic, so no actual dopants. The chemical potential lies exactly midway in the band gap, and we just will derive that today to show that's the case. And here, it's plotted in terms of density of states. Sometimes we had it lying down that way and had the density of states going up that way. Sometimes you can put it up vertical and have it that way as well. Okay, so the density of states just come here. And now we're looking at the population of actual carriers. So we have here the intrinsic one, where you have equal numbers of holes and electrons, because remember, the only way you get holes in the conduction band is by exciting electrons out of the valence band that go into the conduction band. Therefore, you must have holes, equal number of holes left in the valence band. So you've got the same size there. N-type semiconductor, it will have some small holes still present. And if you're doping, with an N-type dopant, then you're going to get a larger number of electrons in the conduction band. Okay. Conversely, here for holes, you're going to have, you'll still have a small, very small concentration of N-type carriers, but a larger concentration of P-type carriers. There's this definition. I don't want to say too much about it, but you may come across it. A degenerate semiconductor, and wonder what that is. It just means one that's been really doped a lot, and it's kind of lost its semiconducting character. Like, we want these dopants to form discrete levels containing electrons or holes, but when one dopes it so much, you can kind of imagine you will actually start to form electron bands in the vicinity of the band edges. I don't want to say too more about that, but that is a material that's got a very high level of doping, so it acts more like a metal than a semiconductor. Just a definition. Okay, so there's a couple of main things that we need to get through today. Going back to density of states. Okay, going back to lecture 3. Remember this plot here for the free electron, like density of states, and we had this expression here, and this relationship on energy goes as the square root. Remember that? We're going to use that to estimate the population of electrons in the conduction band and holes in the valence band. We are going to say that these particles in the vicinity of the band edges behave like free electrons. Okay? So that's why we are invoking this kind of formalism that we had earlier on. Now, okay, here's a picture of our band structure just in the vicinity of the band gap. We define here EV, that's the energy position of the valence band maximum. So all of this band is completely filled with electrons up to here. Then you have your band gap, your forbidden gap where no electrons can exist, and the conduction band EC here. And the energy gap is just the difference of the conduction band minimum and the valence band maximum. So for here, the electrons in the conduction band, we are going to say they behave just like free electrons, but we are going to replace the mass of the electron with the effective mass, okay? So that sort of captures the curvature of the bands there. And we have here the square root of EC, conduction band minimum, and our energy is going to be somewhere above that, okay? So we're just concerned, this expression is just concerned with the electrons up here. Same thing for the valence band density of states. Here we're just concerned with energy E from down here, or from here down to wherever, okay, just in this part of the band. So we have EV, the valence band maximum, minus whatever energy we are at. Just want to say a word that we're going to be working with a chemical potential, which varies as a function of temperature and concentration. Remember in a metal we just had the Fermi level, and it was defined such at T equals 0, it was the state that was the topmost filled energy level. And remember this, we had the Fermi-Dirac distribution. We're going to use this again. We are going to rename it, just so that you're aware, not F here, but N, to reflect that we are talking about electrons, okay? So this is the way we get the temperature into our distribution of population of holes and electrons. So yeah, this is what we use, the chemical potential here. And just to make you aware, when you're reading the literature, it's not very well precise what people use for this energy. Sometimes people use chemical potential, sometimes people just call it the Fermi energy, and sometimes people call it the Fermi level, even though in a semiconductor it's a little bit more complicated. And we should adopt the chemical potential notation. That's probably the best. Okay. So if we have a look at this here, what we can do, now how on earth are we doing this? This is the density of electrons in the conduction band, and it's a function of temperature, okay? Because remember, this thing here is now that was our Fermi function. I think I just renamed that, the Fermi function. And this is our density of states, okay? So we have the shape of our density of states, and now we are populating using the Fermi distribution. This beta, as before, is 1 over kBt, Boltzmann constant and temperature. So when you look at this expression here, okay, so this is the Fermi distribution, this is your density of states. We're going to assume or look at the case where the energy minus the chemical potential is a lot greater than kBt. Remember, kBt is a very small number. It's only 0.025 eV. So this term here E minus the chemical potential is the energy, which is a variable, and the chemical potential will be somewhere in the band gap. So it's a fairly safe approximation. It just means that in this exponential here we can neglect 1. Okay, so you can rewrite this as just e to the minus beta and the argument there. So just turning it upside down if you get rid of that. Okay, so now just plugging back in for the G, our density of states that we had from lecture 3, putting the actual terms in. And so we just have this factor here entering instead of this mess. And this term here comes from the rest of our density of states. Remember that square root of 2 variation here. And so you can guess what we're going to do. We're going to just try and integrate that thing and get a nicer expression. Okay, that's just to show you that the Fermi level is in the gap somewhere, and its position can vary. And we'll see later that at t equals 0 for an intrinsic semiconductor, it's exactly halfway in the middle of the band gap. Okay, so let me just see what we are doing next. Okay, so it's a bit of a trick. I mean, I didn't discover it, obviously. But anyway, we want to integrate this expression here. So if you multiply both sides by this, these two exponential terms, which obviously equal 1, it's somehow easier to solve. So we're going to see how that happens. So, okay, just multiplying 1 by the other side, that's okay. What we're doing here is we're taking this positive part and sticking it outside of the integral because it's not dependent on the energy variable. And then we're just left with this term here and our density of states square root function there. And what you end up with is that thing there. I want to go through the working with you so that I know you can do it by yourself, but you probably won't. So I'm going to do it here. Okay, so let's yeah. Oh, probably. Yeah, you can ask me afterwards or email me. Yeah, I've got it here. We can have a look at that later. Let me just focus it for you. That's a bit nicer. Okay. Okay, so remember we had this on the other side, and there was some prefactor there, which I won't bother writing out. The thing that we are wanting to work through is this integral here, e minus e c to the half e to the minus beta e minus e c. So one can do that if we say let x equals beta e minus ec. This could be a question on the exam to derive this, couldn't it? But it's not going to be, so I was just thinking, yeah, it could be. It's just math, so. Okay, then e minus ec equals x over beta. We need the x dE, so that just equals beta And so we can then get dE equals 1 on beta dx. So we can rewrite the integral in a bit nicer way. No, I don't need that. So we get 1 over beta dx, x over beta to the half e to the minus x. Okay, so let's get rid of that beta from under there. So we then get 1 over beta to the 3 over 2 integral of dx x to the half e to the minus x. Does anybody know offhand what that equals? Probably not, right? Anyway, it equals the square root of pi over 2. So this is the main thing that you can just look at that from your tables, right? So basically then we are happy. We can write the full thing out, 2m E star 3 over 2. This is from our density of states thing. Remember we had the e to the beta mu minus conduction band energy from when we multiplied both sides by those two exponential terms that equal to 1 when they were multiplied together. That's this thing. Now we have beta 3 over 2 square root of pi over 2. So then you can just tidy that up. And m star mass of the electron 3 over 2 pi to 3 over 2 h bar cubed beta 3 over 2 e to the beta mu minus EC, and we are basically there. 1 over 4 2m E star kBT, getting rid of the beta now to be kBT, pi over h bar squared 3 over 2 e to the minus beta EC minus mu. Yeah, that will give you the density of electrons in the conduction band. Okay. So you can see it's straightforward once you know how, of course. Everybody got that? Okay. So that's, a red box thingy. So it's an important equation. And then we're going to do the same thing for the holes, okay, as you would probably expect. So in this case here, okay, the important difference here is we have kind of the same procedure. We have now for the P, which means holes, we are integrating from minus infinity, as you can see, all the way up to the valence band maximum. We have the density of states from before, but in this case, you can see we have 1 minus the Fermi function. And that's because that was giving the probability that an electron was occupied at a particular temperature. So we are wanting holes, so we want 1 minus the probability of an electron is occupied. So that gives us the probability of a hole is there. Just rewriting that like that, just make a common denominator. And then we're going to do a similar approximation. We are going to assume, in this case, that our chemical potential here is is above the top of the valence band, and so this will be actually a negative number. Okay, so that's why it's very, very small, because we are doing the energy from down here minus the energy up here. So this is negligible. So we cross that out from under there, and they're just left with this top part here. It's a kind of valid approximation to make. And if you do the same thing that we did before, multiplying by that e to the whatever times e to the whatever and equals 1, you can derive this expression for the holes. Okay, I won't do that again because it's boring and you know how to do it now. So this is the important equation for the density of holes. So this is another important expression. It's called the law of mass action. What we've done is just multiplied the density of electrons by the density of holes at a particular temperature. And when you do that, you get this expression here. It's just straightforward. The only thing we've done here is to replace the difference in conduction band minimum with the valence band maximum and just call that the energy gap. Okay, that's just the band gap. Put there. Okay, so we're going to go a little bit further. Remember, we wanted to derive that the chemical potential was in the middle of the band gap at t equals 0. So this is now on the way to do that. And if we're considering intrinsic semiconductors, so the number of electrons that are excited up into the conduction band must equal the holes that are left behind. So P equals N. And here we are just dividing the expression for N with the expression for P. Here we multiplied them. Okay. Now we're dividing them by each other. And so we end up with this expression here. It's again, no tricks in that. This just comes out as an expression here. And what you can see already is that we've got the chemical potential in there, mu. We've got the effective masses of the holes and electrons. We've got the temperature, which we know, and we've got the valence band maximum and conduction band minimum in there. So this is, from this we get the expression for the chemical potential in the next slide. Yeah, so we have that expression. Now we just take the log of that, get rid of this exponential here, and rearranging, you get this expression for the chemical potential. So that when you are at exactly t equals 0, this term disappears, and it will be located exactly halfway between the conduction band minimum and valence band maximum. Okay, so at t equals 0, it goes to the middle of the band gap. And yeah, often when people make plots from their research of electronic band structures and density of states, very often you will see that they have put the energy 0 in the middle of the band gap. It's completely arbitrary, really. Sometimes you can also put it at the valence band maximum. So in the literature, you'll probably see, you know, some of them put it at the energy 0 at the valence band maximum, and some will put it in the middle of the band gap. And for the case of intrinsic semiconductor, where the concentration of electrons is equal to the concentration of holes, we have Ni equals Pi, and that's equal to the square root of the, if you have a doped system, you might have a different number of dopants than just in the intrinsic material. Same thing for the, if you have a, I mean, you always have some P and N concentrations, but if you're doping with electrons, your concentration of electrons N will be much, much bigger than this small p. And then that's just, again, from the law of mass action that we derived before. So these are kind of important equations, yes, which you will probably use. I've forgotten whether it's the assignment or whether it's the quiz or whatever, but yeah, this is where you will get the equations to do that. Okay, so let's just have a look at some real numbers. Basically, if you just say that all this horrible prefactor is roughly 10 to the 25, just for now, not forever, then you can see how the concentration varies, for example. In this case, what have we got? Yeah, it looks like we're dealing with N electrons here. So we've got indium antimonide, which has a very small band gap, okay? So it should be really easy to get good populations. If you substitute in T equals 150, okay, you've actually done the actual calculation here. Or maybe I just left that constant and just varied the temp. I can't remember, it doesn't matter. What you see is that at 150, you get quite a respectable number, but as you go higher in temperature, it goes up a little bit higher, okay? Silicon has a larger band gap, and as you'd kind of expect, the concentration of dopants is smaller because you have this exponential factor here with the band. The bigger the band gap, the smaller your concentration will be. If you increase it to 300 K, you actually get quite a big jump up here to 2 times 10 to the 16. Diamond, which is, of course, very stubborn, very big insulating gap, you are not going to really do anything. 6 times 10 to the minus 68, and yeah, to the minus 21. Yeah, you just won't get any carriers there. So you can really see that it depends sensitively on the band gap, how many carriers you get. So it's really important. This is why everyone talks about band gap engineering. If you can control the band gap and dope it with particular states, you've got a lot of control over your material. Okay, we'll just have time to do a rough little problem here. What have we got? We've got silicon at 300 K under equilibrium conditions. We will always be at equilibrium conditions in this course, okay? It just means that the system is completely sort of equilibrated in terms of atomic positions and dopants. Okay? So you don't need to worry, that's just a word. So it's doped with boron to a concentration of 2 times 10 to the 16 centimeters to the minus 3. The first thing to notice is sometimes people use meters cubed and sometimes they use centimeters cubed. Now you're given that the intrinsic concentration is 1 times 10 to the 10 centimeters to minus 3. So the first question, what are the electron and hole concentrations, N and P, in this sample, and is it N or P type? Okay, so let's first of all have a look at, so we've got silicon, we're going to dope it. Okay, it's doped, okay, this doesn't really matter, but it's doped with boron to 2 times 10 to the 16 centimeters to the minus 3. If we just remind ourselves what boron is, the atomic configuration, it's like the helium atom, but then we've got some more states. We've got two S states which are filled completely, and we've got two P states which only have one electron in. So it's got three valent states, electronic states. So that already will tell you it's an acceptor, right? Because it's got one less than silicon. So that's okay. It's an acceptor, and we call materials with acceptors, they are doped p-type. So find donor concentration. We can use the law of mass action that we have just derived, and we know that the intrinsic concentration multiplied by the of electrons and holes is equal to the actual N concentration that has been doped and the resulting P, or vice versa. Okay, so with that, we are given other information about the intrinsic concentration, that is equal to 1 times 10 to the 10 centimeters to the minus 3. So if no dopants are there, you will still have some intrinsic concentration. You can see it's not a big number in terms of doping a material. This is not a big number. So we can just figure out N I times P equals NP, so that will equal 1 times 10 to the 20. Okay, that's just from the intrinsic squared. And we have been given P, right? So P was 2 times 10 to the 16, 1 times 10 to the 20. So we can get N is equal to 5 times 10 to the 3 centimeters cubed, which is what we were after. Is that not what we're after? Given the intrinsic constant, what are the electron and hole? Okay, so that's the electron concentration. And so the whole concentration is, okay, well, obviously we've already been given that. All right, so now we've got this material that's doped with acceptors, right, with that concentration. And then somebody comes along and dopes it now with phosphorus to a concentration of 6 times 10 to the 16. And so now we have to figure out what now are the N and P concentrations. So we know phosphorus is a donor. So it's doped now with so N is given to be 6 times 10 to the 16 centimeters to the minus 3. So they've put that much number of dopants, electrons, into our system. So we had that it was P-type before, with 2 times 10 to the 16. So now it's got 6 times 10 to the minus 16 of the opposite sign. So since 6 times 10 to the 16 is greater than 2 times 10 to the 16, remember these were holes. Now these are now electrons that have been doped. It means that we now have N-type material. We've just got more electrons than holes now. Okay, so it's now N-type with a concentration of 6 minus 2, because those electrons have now been annihilated by the holes. So we have n equals 4 times 10 to the 16 centimeters cubed. And how to find out the new P, again, find new P, new hole concentration. We again use the mass action, law of mass action, and we know NP equals NI PI, and we know that that was 1 times 10 to the 20, the intrinsic concentration squared, so that we can figure out now our new P-type P concentration as 1 times 10 to the 20 divided by 4 times 10 to the 16, which gives us a very small number of just 2,500 holes per centimeters cubed. Okay, so that's just an example to sort of show how those equations work that we've just been looking at. I just will finish. Just want to sort of show you just something about what the research is, one aspect of it that people are doing, at least from the theoretical side, but theoreticians often work with experimentalists. Okay, so you can take a material, you know. In this case, I've taken one from the literature that's aluminium nitride. It's part of the gallium nitride family for the laser diodes and LEDs. And, you know, some 20 years ago now, I guess, there was a lot of research going into it. And as I said before, for many kind of semiconductors, native defects would kill a device. But for these nitrides, they weren't so affected by the defects. And so people wanted to understand a lot about the defects. So if you have this material, there's various native defects that you can consider. As I said earlier, you could consider a nitrogen vacancy, where you have a nitrogen atom missing, or an aluminium atom missing, or nitrogen sitting on an aluminium site, or an aluminium sitting on a nitrogen site. These are called anti-site defects. You can also have interstitials. You could have too many nitrogen atoms. And you might have a nitrogen atom just lurking about, like in the crystal structure somewhere. Conversely, you might have an extra aluminium atom. These are all so-called native defects. And so what you can do is you can calculate using, you know, really accurate methods now on supercomputers around the world. Get very accurate and calculate big systems, not just small systems I can show. This just shows the unit cell. Like your cell is actually bigger in the calculation. But what's the point? The point is you can calculate the dopant, no, in this case defect, sorry, the defect levels, and you can see where they are in the band gap. You can also calculate if they're occupied or unoccupied. Occupied is a black dot, unoccupied is a circle. And then what the experimentalists can do, they can come with their optical techniques and fluorescence or whatever, and they can measure information about states in the material. And if they find, you know, a signs emission from these kind of positions in the band gap, then, you know, that supports that, oh yes, it might be, you might have here an aluminium vacancy, for instance, if you've got, so this is an acceptor. Okay, it's really close to the valence band maximum, and it can accept electrons as holes here. It can jump up into there. Okay, so that's what a lot of people doing the computational side do. They might do that and work with experimentalists. But that's not the only story, is it? I mean, you can calculate this, but what happens, they may not form energetically, okay? So what people do is they also calculate the formation energy of these defects. I won't go into details, but the lower the line here, the more likely the defect is to form. So, for example, if an experimentalist thinks, oh, I've got lots of antisites in my crystal, you can go along and show, look, hey, it's really unfavorable. And, you know, it's not that side after all. So, anyway, I just want to show you some other further interesting related work on the semiconductors. Okay, I better leave it there. I think time is going. So one more lecture on Friday, and then, well, I will still be here for next week, but the other people will go to a room to be decided and notified on. And the last lecture, I think we will maybe recap a little bit about exam, you know, what could be on the exam and things like that.